So welcome, structural isomerism of alkanes. That is the focus of this lesson. So if you have not subscribed to our channel yet, then please quickly do so. But what exactly is structural isomerism in alkanes? You see, in an earlier lesson, we've already defined what structural isomerism is. So if you have not watched that lesson yet, then please check the description under this video to have access to that lesson. Or better still, you can check the entire playlist of videos that we already have so that you follow us systematically from the foundation model till now. So, what is structural isomerism of alkanes? Or what are structural isomers? You see, as discussed earlier, structural isomerism occurs when compounds have the same molecular formula, but their atoms are connected differently. So the atoms are differently connected. There's difference in connectivity of the atoms. That is structural isomerism. And the examples we used, or the example we used was C₄H₁₀. So for the first one, there are 3 carbons, and the 4th carbon is sticking out from the middle carbon. And then the other one, the 4 carbons are arranged in chains. All of these was discussed in an earlier video, so please go watch it. But what is the focus or the objective of this lesson? We are going to guide you through writing the various isomers of a given alkane. And we are going to use the simplest example as possible. But trust me, if you understand that well, you'll be able to write the structural isomers of any given alkane. I give you my words. I mean any given alkane. So let's get started. So write all the structural or chain isomers of pentane. Pentane is C₄H₁₀. So if you see write all the structural isomers of pentane or write all the chain isomers of pentane, the question means the same. So first things first. Pentane C₄H₁₀. So to write the first isomer, what are you supposed to do? Step 1. Check the number of carbons present. How many carbons do we have? We have 5. So let's write that. So 1, 2, 3, 4, 5. Count them and see. We have 5 carbons present. And how many hydrogens do we have? We have 12. 12 hydrogens present. So this is what you are going to do. All the carbons must have 4 bonds. So spread these 12 carbons or 12 hydrogens around the 5 carbons. So let's go. We have 1 here, 1 here. We've gotten 2. We are left with how many? 10. So we've already spread 2 hydrogens on the carbon. So we are left with 10. The remaining 10, 5 goes to the top. Count them and see. We have 1, 2, 3, 4, 5. So 5 will also be at the down. 1, 2, 3, 4, 5. So 5 down, 5 top, 10. One side, giving us a total of 12. So we have C₄H₁₀. This is pentane, or called N-pentane, meaning normal pentane. Now, the next isomer to write, what do we do? Well, look at this. You can decide which of the CH3s to cut. But for this example, I'll cut from the extreme end to the, I think to the right. Yes, to the right. So that is what I've put that, is it rectangle or whatever, around. So we assume we are going to cut that CH3. This carbon bonded to 3 hydrogens is also known as CH3. And you see that behind the CH3 there's a dash. That means the CH3 can bond anywhere when cut from that side. So when you cut this CH3, you can use it to replace any of the hydrogens, any of the remaining hydrogens, except the extreme ends. So you see the hydrogens, those 4 hydrogens, I've put the rectangle around. You can use them, you can use the CH3 to replace any of these 4 hydrogens, except the ones at the extreme end. Why? Because if you put the CH3 at the extreme ends, use it to replace any of the hydrogens, you've actually not changed the molecule. So keep that in mind. So if you cut the CH3 this way, we can use it to replace any of these 4 hydrogens. So what do? Let's assume we use it to replace the circled hydrogen. So what does that mean? So we are left with 4 carbons. Why do we say 4 carbons? Remember, we've cut the CH3, so the 4 remaining carbons are the ones here. Good. Now what do we do? The hydrogen that we have circled, we'll use it to replace where the CH3 is. I think that should make sense. I think the English I just put makes sense. So use that hydrogen to replace the position of the CH3. And then the CH3 goes to where the hydrogen was. Please take your time to understand that very well before you move on. So immediately you are done with these main steps. The only thing to do is to replace the remaining sides with hydrogen. You are done. Is that not simple? Yeah, that's simple. So I'm going through the steps again. Pick any of the extreme ends of the CH3, cut it and use to replace any of the middle hydrogens. If you're able to do that, you are done writing your first isomer. Now, when you are done with this, to write the next isomer, we go through the same step again. So what do we do? By the way, the name of this compound is 2-methylbutane. 2-methylbutane. By the way, if you are just watching this video for the first time without watching our earlier lessons on alkanes, you wouldn't understand how we got to this name, 2-methylbutane. Yes, so if you want to know how to name straight chain alkanes or branching alkanes or alkanes in general, please check the description under this video to have access to the playlist, so that when you see us naming these compounds, you'll not get confused. Okay, so now let's continue. So this is 2-methylbutane. Now what is the next isomer we can write? We go through the same steps. We cut the CH3 at the extreme ends. For now we have 2. We have one at the end to the left and another to the right. We can cut any of them. Ideally, it is best to cut the one to your left because that will give you the best chance of writing the next isomer. So let's do this. Let's cut this particular one. Now, for this time also, we have the option to use it to replace the middle hydrogen below the attached CH3 that is serving as a branch. I think that makes sense, right? Good. So now let's come back. When we cut this CH3 at the extreme end, the straight chain will be left with only 3 hydrogens. So this is what we have. Now what do we do? The circular hydrogen can be moved to replace or come in place of where the CH3 was. So we have it this way. So the circular hydrogen has come to where the CH3 was. Then the CH3 will move to where the hydrogen was. I think we are done with that. Then after that, we have to make sure the remaining carbons have their 4 usual bonds. So let's apply the remaining hydrogens. Now at this point, you can still count the number of carbons and hydrogens in each of the isomers you've gotten. And you realize that they are all C₄H₂. If you count the number of carbons, you will get C5. If you count the number of hydrogens, you will get H12. So this compound is 2,2-dimethylpropane. 2,2-dimethylpropane. So still, if you've not gotten how we named it, you can watch our lesson on naming of alkanes to understand how we came up with the names. Is there any isomer we can write again from C₄H₂? Well, if you try to write any other isomer, you wouldn't get it right because you end up just writing another compound that is similar to the ones you've already done. So that means C₄H₂, which is pentane, has only 3 isomers. So the first one is N-pentane, meaning normal pentane. They have 2-methylbutane, then 2,2-dimethylpropane. All of them have the same molecular formula C₄H₂, but their structures and the way atoms are connected are different. So if you really understood what we just did, let's look at the next example. C₄H₁₀. So I dare you to pause the video and write all the possible isomers and see if they correspond or match with the one we will get. So write all the structural chain isomers of hexane, C₄H₁₀. So this is the first isomer, N-hexane. Check for yourself. Check the number of carbons. We have 6 in total. Then we have 14 hydrogens around. Count, verify, and you'll see that that's exactly what you have on the screen. Now, what is the next isomer of this N-hexane? Cut one of the CH3s, either the one to your left or to your right. Cut it to replace any of the middle hydrogens. So if you do that, you are going to get 2-methylpentane, depending on where you place it. But I have decided to place it on the second carbon from my right. Yes, from my right. That's the second carbon from my right. So if I place it there, that will give us 2-methylpentane. Now my next stop is not to cut any CH3, but I see the CH3 where I have placed it. I can move it. I can shift it to the middle H or to the H beside it this way. Good. So that gives us what? That gives us 3-methylpentane. So writing isomers, so interesting. When you cut one, you can just shift and see. If you shift and it gives you an entirely different compound, then that is also an isomer. For the next stop, we are going to get 2,2-dimethylbutane. How did that happen? Look at what we did. We cut the CH3 at the right again, either at the right or the left. So you cut at the right and then place it on one of the middle hydrogens that we have the liberty to place on. And when I place it there, we got 2,2-dimethylbutane. Is there any other compound that we can get? Yes. What can we do? We can decide to just shift the position of one of the CH3 in this way. So if we shift the lower CH3, that's going to give us an entirely different compound. That will be 2,3-dimethylbutane. So these are the possible isomers that can be gotten from C₄H₁₀. So that is isomerism for you. Is that difficult? Someone will say yes, another person might say no, but it's simple. Just practice over and over again until you understand it. Because we were all at one point in time at your stage where these things sounds or seem so strange and difficult to understand. But at this time, we now understand it because you'll be practicing and using it for years now. So I know if you also practice, you will understand what exactly it is. So now let's look at a summary table of the isomers of C₄H₁₀. So take your time to analyze them. You have the IUPAC names and their structural formulas. The diagram or the formulas we had on the previous slide that shows the skeleton or the bonding is what refers to as the displayed formula. But what we have here is the structural formula. If you do not know how to convert structural formulas into displayed formulas or displayed formulas into structural formulas, there is an earlier lesson we've already recorded. I'll leave a link to it in the comment section or in the description so that you can actually have access to it and not miss out on any important detail that I've already taught. Good. So this brings us to the end of our lesson on isomerism of alkanes. Now the next thing we want to consider is the structure and bonding of alkanes. Structure and bonding. What kind of structure and bonds do we have in alkanes? If you do not want to miss, then you know what to do, right? Subscribe to the channel, hit the like button, and share the video with other students that you know. See you in our next lesson.